Okay, so now we're going to move on and look at estimators. And what we want to do is to be able to show whether or not we have a biased estimator. For this, we actually need some considerations. So we'll consider that all sample observations have the same mean and variance as the population that they were taken from. So the sample observations I've denoted here as xi. So every item in my sample, every one of the sampling units, we say has the same mean and variance as the population. So the expectation of xi is mu, and the variance of xi will be sigma squared. Okay, let's go ahead and think about x bar. So x bar, we know its formula, sum of x over n, or I can write it as 1 over n multiplied by the sum of x, which I can expand to show the individual sample items that were being added together. And then we go ahead and take the expectation of both sides. So the expectation of x bar equals this expression. I can take 1 over n outside of the expectation. And then I have the expectation of the sum of the sample items, the sampling units. So I can go ahead and say it's the expectation of each of them individually. And as I started, the expectation of any sampling unit is actually just going to be mu. The expectation of xi is mu. So all of these mu's make n mu, and I simplify to mu. So the expectation of x bar in this particular case, the fact that the expectation of x bar equals mu tells us that x bar is actually a good estimator of mu. We've done the algebra, we've done our manipulation, and we ended up with exactly the population parameter we were trying to estimate. If it was off, then we would say it's a biased estimator. But because it was exactly on mu, x bar is an unbiased estimator of mu. This means that any particular calculation of x bar is likely to be an unbiased estimate of the population mean, mu. We can actually calculate the bias that an estimator might have. So if we have an unbiased estimator, the bias is 0. If it's a biased estimator, we calculate the bias by taking the expectation of the statistic and subtracting the population parameter. So the expectation that you would calculate minus the known parameter leaves us with the actual bias. So let's continue to look at x bar. And this time, I want to try and see what the variance of x bar might be. A low variance means it's a consistent, reliable value. A large variance means there's a lot of variety and variability in the estimator, indicating how likely our estimate is to be close to the population parameter. So a low variance is likely to be close to the parameter. A high variance, it's less likely to be close to the parameter. Okay, so let's get back to thinking about x bar. So I'm just going to write the expression out again. Sum of x over n. We like the form 1 over n, sum of x. We're going to write the sum of x as an actual sum of the observations from the sample. All right, now I'm going to take the variance of both sides this time around. Variance of the left, x bar, equals variance of the right, 1 over n, and this bracket. Okay, if you remember, if I have a constant inside the variance bracket and I take it out, it needs to be squared. So I've got 1 over n squared times variance, the sum of the observations. And as we said before, the variance of one observation should match the variance of the original population distribution. So we'll go ahead and say that that's the variance of x1, variance of x2, all the way through to variance of xn. And I think you'll recognize this next part. I've got 1 over n squared, and each of these variants of an observation is going to be sigma squared. Okay, and I've got n observations, so that's n sigma squared. All right, good. Let's just deal with the outside. I expand that bracket, and I can see that n's will cancel. My variance of x bar is going to be sigma squared over n. Variance of x bar, sigma squared over n. If you notice here, the variance is dependent on the sample size. And actually, as the sample size increases, as n gets larger, the variance is going to be smaller and smaller. It's going to represent more consistent values. It's going to be more reliable. So actually, as n gets larger, the estimator actually gets better. So as n gets larger, the estimator gets better. And that kind of falls in line with what we've always thought about sample sizes. The larger the sample size, the more reliable the results you get. So now that we have an expression for the variance, it's only natural that we think of the standard deviation. The standard deviation of an estimator, we're actually going to call the standard error of the estimator. And it's just the square root of the expression we got for variance. So it's the square root of sigma squared over n. I'd much rather write that as sigma over root n. Okay, and one more version, which we'll get used to, s over root n. In this case, s being the sample standard deviation. And we'll talk more about that in the next section.